This is Algebra 2, Unit 6, Lesson 9 on modeling with quadratic functions. Now, we've used quadratic functions to model a wide variety of real-world applications. We are going to focus in this lesson on using quadratic models to predict and to optimize. So our solution will depend on either the intercepts or the turning point of the quadratic model. So we're going to focus on some parts, specific parts of the quadratic equation. All right, so here's our first exercise. An object is fired upwards with an initial velocity of 112 feet per second. Its height in feet above the ground as a function of time in seconds since it was fired is given by the equation h of t equals negative 16t squared plus 112t. So at what height was the object fired? All right, so let's think about this for a second. The height, feet above the ground, is a function of the time in seconds since it was fired. So when the object was fired, at what time was it? Well, that was when t was equal to 0. So the height, when t is equal to 0, would be h of 0. So h of 0 is equal to negative 16 times 0 squared plus 112 times 0. All right, so that would be 0 squared is 0 times 16 is 0 plus 112 times 0 is 0. So this is all going to be 0. So at 0 seconds, with the starting time, it will be 0 feet in the ground. Now that makes sense if you think about it, because remember, if this is h of t equals negative 16t squared plus 112t, this is technically plus 0 on the end, and that would be your c value. All right, so let's sketch a general curve of this equation below. All right, so here is my axis. We know it's going to start at 0, 0. At 0 time, it's going to be 0 feet in the air. All right, now this is negative 16t squared plus 112t. Now remember, this is your leading coefficient is negative, so I mean the parabola is going to be pointing down. It's going to look like this. All right, so what we want to do is draw our parabola. It's going to go up, and it's going to come down like this. All right, so this is our height, and this is our time. All right, so it's going to start at 0, it's going to go up, and then it's going to come down. Now this says, algebraically, find the time that the rocket reaches its greatest height and the maximum height. Label these parts that you have on the graph. Okay, so the greatest height on this parabola would be right here. It would be the vertex of the parabola. Now, in the last lesson, we talked about finding the vertex by using the axis of symmetry. So algebraically, find the time that the rocket reaches its greatest height and the maximum height. So the time, it would be the x, is negative b over 2a. All right, so we need to know in our formula, here's our parabola, h of t equals negative 16t squared plus 112t. What is the b value? Well, the b value would be 112, because that is ax squared plus bx plus c. The b value is going to be 112. So this is actually going to be negative 112 over 2 times a. What's a? A would be negative 16. All right, so this is negative 112 over negative 32, and divided out, it comes out to 3.5. Now this is the time, so this is at 3.5 seconds. So that means that this time is going to be 3.5 seconds. All right, so at 3.5 seconds, it's going to reach its maximum height. What would be its maximum height? Well, if this is 3.5, we need to figure out the y that goes with it. It would be h of 3.5. All right, so plug that in. Negative 16 times 3.5 squared plus 112 times 3.5. All right, now I can do that on my calculator pretty easily. Negative 16 times 3.5 squared plus 112 times 3.5. And that tells me it should be 196. So at 3.5 seconds, it will be 196 feet in the air. All right, so that would be the greatest height is 196 feet, and it happens at 3.5 seconds. All right, algebraically determine the time when the rocket reaches the ground. Okay, So remember our formula is h of t equals negative 16t squared plus 112t. We are looking for the time, so we're looking for t. So we need to know at what height we're looking for. Well, if algebraically when the rocket reaches the ground, at what height is it at? Well, that means that h will equal 0. So if we take our equation, negative 16t squared plus 112t is equal to 0, quadratic equation. All right, so make your life easy. Divide everything by negative 16 first. And it does divide out evenly, believe it or not. This works out to be t squared minus 7t is equal to 0. Oh, that factors. It factors by GCF. T times t minus 7 is equal to 0. So that means t is equal to 0. And t minus 7 is equal to 0, making t is equal to 7. All right, so at 2 times, the rocket is at 0 feet. The starting point would be at 0, 0. The ending point would be at t equals 7. So this value would be 7. And that makes sense when you think about it. Remember, the vertex is at the halfway point of the parabola. If that's at 3.5, this would have to be at 7. So at 7 seconds is also at 0. So that is figuring out algebraically, figuring out the vertex and the time. We just did the sketch. All right, let's try another exercise. A skateboard half-pipe ramp has a shape in the form of a parabola whose equation is y equals 0.06x squared minus 1.2x plus 7, where x represents the horizontal distance across a 20-foot wide half-pipe, and y represents the ramp's height above the ground in feet. With the help of your calculator, sketch a graph of the height part below, label its height at the endpoints and its minimum points. Okay, so let's see if we can do that. Here's my sketch. All right, now, first of all, which way does this parabola open? Well, this is 0.06x squared, positive a value. Leading coefficient is positive, so that means that it's going to open up like this. So I know that for sure. All right, now, we want to start out on our half pipe on the y-axis somewhere. So that's going to be the y-intercept. Now, what part of the equation is the y-intercept? Well, it should be the 7, because if x is equal to 0, that means when I plug this in, 0.06 times 0 squared minus 1.2 times 0 plus 7, we know it's going to start, this is going to cancel out to be 0, and this is going to equal 7. So 0, 7 is going to be our starting point. All right, so we know our parabola is going to go down and then come back up. All right, so the maximum, or the minimum is going to be down here. It's going to be the lowest point of the ramp, and the maximum, and then it'll go back up to the point out here. So what we have to figure out is what these values are going to be. So its height at its endpoints and its minimum point. Well, we said this is going to be how wide? It's going to be 20 feet wide. So going out from here, this is going to be 0, and this is going to be 20. All right, so just for guess, what do you think this is going to be right here? Well, remember, this is the minimum point. It's going to be 10. Okay. All right, so now I know that this value is 7. This value has got to be 20. All right, so let's check our window and make sure that our parabola looks like it's supposed to. All right, so here's my window, y equals. All right, I have 0.06x squared minus 1.2x plus 7, and I want to set my window. My x's were between 0 to 20. That's my horizontal distance. And then my y's, I went from 0, 7 was my y-intercept, so I'm going to leave it at 10, because that'll go up enough that I can see the window. All right, so let's graph our window and see if it looks like it's supposed to. Yep, that looks like what we had on our paper. All right, notice here this is 7. If I look at my minimum point, I can calculate the minimum by picking number 3. I'm going to go left and right a little bit. Left here, enter, right here, enter, and I can find my minimum value. 0.999 is going to be at 10. All right, so this is going to be at 10 right there. And you can see on the calculator that is actually at 10.1 is my minimum point. So this is at 10.1. All right, now algebraically we can do this. All I have to do is plug in x equals 10 to figure out that this is at 10.1. All right, so I know y is equal to 0.06 times 10 squared minus 1.2 times 10 plus 7. And when I work that out, it does come out to be 1. So this is 10, this is 1. All right, so there's the sketch. Now notice we did the sketch without even having to put it in the calculator, just by working out what we knew. Let's try the next problem. The Crazy Caramel Corn Company has determined that the percentage of kernels that pop rises and falls as the temperature of the oil in the kernels are cooked in increases. It modeled this trend using this equation. P equals negative 1 over 250 t squared plus 2.8 t minus 394. All right, P represents the percent of kernels that pop, and T represents the temperature of the oil in degrees Fahrenheit. Algebraically, determine the temperature at which the highest percentage of kernels pop. Also determine the percent of kernels that pop at this temperature. Okay, so if I'm thinking about this problem, this is a parabola. It says the percentage of the kernels pop rises and then falls as the oil and cooking increases. So this parabola would be going up and then down. So if I'm looking for the highest percentage, I'm actually looking for the vertex. So let's figure out the vertex. Now it's x equals negative b over 2a, but in this case it's going to be t equals negative b over 2a. All right, so what's b? B would be 2.8. So negative 2.8. 2a, a would be negative 1 over 250. Oops, 250. All right, so if I multiply this out, I get negative 2.8. Negative 2 times negative 1 over 250 is negative 0.008. And divided out, this is equal to 350. All right, so T is in degrees Fahrenheit. So this is 350 degrees Fahrenheit. So our temperature at 350 degrees Fahrenheit will be the highest percentage. All right, now the P, the percentage of kernels that pop, is P at this temperature. So we would take this equation, P equals, and plug in 350. Negative 1 over 250 times 350 squared plus 2.8 times 350 minus 394. All right, so I have this in my calculator already. Negative 1 over 250 times 350 squared plus 2.8 times 350 minus 394 is 96. So this actually equals 96. And since this is P, it's 96% of the pop, corn pop. So it says P represents the percent of the kernels that pop, T represents the temperature of the oil in degrees. So at 350 degrees Fahrenheit, 96% of the kernels pop. Okay, so if I was going to sketch a curve for P is greater than or equal to 0 and label your window. All right, so here is my curve. I know it's going to look like this, is what it's going to look like. All right, so I want to sketch for P is greater than or equal to 0. So if I know my maximum at 350 is going to be 350 degrees when 96% of the kernels are going to pop, I know that 350 has got to go in the middle. And my maximum would be 96 would be up here. So what would be a good window to use? Well, let's do 0 to maybe 100. That would be a good window. All right, so if this is 350, halfway, I have to go to at least what? I'd have to go to at least 700. So that would be halfway, so I'm going to go to 700 out here. Okay. All right, so this is going to be my T. This is going to be my P. So let's go to my calculator and go to y equals, and I have negative 1 over 250. I'll use x squared minus, or plus, sorry, 2.8 x, and then minus 394. And then I'm going to reset my window. The x's were from 0 to 700, and my y's were from 0 to 100. And if I do my quick graph, it looks